which model the mechanical behavior, and that's due to a coupling. When I move a wire through a magnetic field, then I can measure some electrically, so there's a real connection between the mechanical properties and electrical properties. And that's not just an analogy, that is a real coupling. Let's go back one page here. Yeah, and that means actually we have here a kind of transducer, and we should write a formula that. And now the question is, let's just go back to some more slides. Yeah, so here is a transducer constant alpha, which transforms, for example, a velocity into a voltage, but also the other way around, it produces a force for a certain current. Okay, and this alpha here comes from Lorentz force, and here we have this factor. B is the magnetic field strength in Tesla, as its unit, and L is the length of the wire. Okay, so this this converter constant we're looking for, B times L. Then the second one we need is the diaphragm mass. Okay, by the way, it's called dynamically moved mass. Okay, then we need the resonance frequency and also the mechanical quality factor. In the resonance frequency, we have mainly mass and elasticity. It also depends a little bit on damping, but okay, mainly mass and elasticity. And in the quality factor, we do find damping. So that means the mass we get directly. Elasticity we can determine from the resonant frequency. And last, we can determine also the damping from this quality factor. Okay, and these are then the three mechanical properties of the loudspeaker. We also have electrical properties, that's just the resistance of the coil, ohmic resistance, and you have some conductivity. Okay. I think we can leave it at that and just try to get all these important data from the data sheet. So, let's write out what we need. The converter constant is B times L. And we have this mass. We need a resonant frequency. We need this quality factor. Then I think it's mechanical, don't know for what. Probably serial. And yeah, okay, resistance and conductivity is over R and L. Then let's take a look at such a. Okay, it's a German data sheet, but okay, it doesn't matter. Numbers and units are international. Okay, so this is the loudspeaker, and blah blah, and here's the technical data. Okay, so a lot of information. Let's just scan through what we need. Okay, so I see something here. Maybe sometimes it's better just to read it from the right side, just looking at units, so you can filter faster what you need. So one thing we need is a frequency with something in hertz. So let's look on the left side what it is. Yeah, bingo, it's the resonance frequency, and it's 43 hertz. So this is the first thing. Which hertz? And what else can we find here? Okay, one thing we're looking for is the mass of the diaphragm. Here is a mass. fragment cannot have a weight of 1 kilogram. No, this is of course the mass of the complete thing. It includes a very heavy magnet, so that's not what we need here. But we have more. When I see here DC resistance, I think that must be the electric resistance. So simply of the coil, no? And that's one of these last points. We have this 5.6 ohms. Okay, and already in the next line you see this mechanical Q. It's just a number, it doesn't have anything more. And but we could look at the definition so that we can understand what is this number, what's the meaning of this number. But first, let's write it down. It's approximately 4.45. I thought we need 3 numbers, so that's 4.4. What does it mean? So we're talking about resonance, and yeah, we have for a loudspeaker parallel elements. So when we look at the impedance, we see here a maximum. So for a certain frequency, the effects of C and L cancel each other, and that means they do not conduct as a sum. So both elements together are something like disruption. So the only thing that remains then is the resistor, and that is the maximum value. For lower frequencies or for higher frequencies, either the capacitor or the inductivity will be a good conductor, so we have lower impedance, but for the resonance we have a maximum, which is defined just by this R. Okay, and then the question is, how fast does it go down for lower and for higher frequencies? Is it a very pointy curve, or is it a very flat curve? And that is determined by the so-called bandwidth, which is defined that our impedance is smaller by a factor of 1 divided by the square root of 2. Or if you calculate it in decibels, 3 dB less. And so on the left side, on the right side, and when we look, that's the limits of the bandwidth range. And this quality factor here is the ratio of the resonant frequency divided by this bandwidth. Okay, and now we know this is a factor of 4. We do not know is good or is bad. Okay, but at least we know these numbers here mean, okay, so the resonant frequency is 43 Hertz, and then the bandwidth should be around 10 Hertz. Okay, so that's what we got here. Electrical Q factor, I don't know what that should refer to, because normally this must be given at a certain frequency. At the resonant frequency, it should be exactly the same as the mechanical Q factor, because well, there is this coupling. Okay, don't know what they mean with that. Okay, so then what else do we have? Yeah, here we have something. Dynamically moved mass, 9 grams. Okay, this sounds more like the mass of a diaphragm itself. So that's probably what we need here for the mass. 9 grams or 0.009 kilograms. Best always to write it in SI units. Okay, and the next line here is the force factor. Well, nice name, force factor. What's that? But this is the, well, it's not the BXL, it's B times L. this is exactly what we need. And we can also see it from the unit. The unit could be terameters, like in terabytes, terameters, but well, that doesn't make sense. So this is probably the product, Tesla times meter, and then that's the unit we need. And it's 5.6 Tesla meter. 5.6 Tesla times meter. Okay, and last one is here the inductance of the coil, 0.9 millihenries. So that's the last value. Okay, so that's an example how we can get from a data sheet everything that we need for our models. And by the way, that's also the content of one of the mini projects. So we would go through such a data sheet and first determine these values. But well, then we've got a model, and the question is this a correct model? And most part of this mini project then is to check if the values make sense, if you can reproduce something with this model of reality. Okay. Let's then do some calculations, at least, that we are doing something productive with this. For the model, we need an elasticity. And I said we can get this from the resonant frequency, which mainly depends on mass and elasticity. And the formula is, good question. We need a fixed formula, or we could always derive it somehow from the electrical case. Okay, but this is just electrically. Okay, but I could go through it electrically. The electric resonant frequency of an L and a C is 1 over the square root of L times C. And we're here in the so-called Fi analogy. It's not just the analogy, it's a real coupling, so we have to use this Fi transformation. And here, the capacity corresponds to the mass. And we can see here the formula. Mass and capacity are proportional. So, in this mechanical formula is, at this point here, is the mass. Then the inductivity L is proportional to 1 over K. Okay, so that means a very stiff spring with a very high K corresponds to a small inductivity. And so it means here that this place we replace this here with 1 over K. Okay, so that's the formula for this resonant frequency. And we already know the mass, and now we can determine this K. Let's put this in a nicer form here. This is denominator of denominator. So K on top, numerator divided by N. That's better. So what you can do is take the resonant frequency, square it. I think I forgot something. I forgot a factor of 2 times pi. Yeah. And of course here the same factor. Let's not forget that. 1 over 2 times pi multiplied with the square root. Oh. So then let's take a calculator and calculate 2 minus we need to square it. So, and, well, that's k over m. We do have m, so we multiply with the mass, and that's 0.009 kilograms. And the result is something like 557, well, let's say, 660 around. Okay, 660. So this is what we can calculate, 660. Well, and the units are, we need a certain force for a certain elongation, so newtons per meter should be the unit. And then the question is, how large is this first of all, how large is this damper constant B, the mechanical damping? Okay, so there was the formula here in this exercise sheet. The quality factor is 1 over B multiplied with the square root, and again we have mass and K. And okay, so we want to calculate B. And I think we do this in one step. So multiply B on the left side, divide quality factor down on the right side. So we have the square root divided by quality factor. Square root of n times k, and then divided by q and s. At least I think it should be. Okay, and then again, let's see, the calculator tells us. So mass 0.009 kilograms. Applied with 660 newtons per meter equals this with some unit. Then we need the square root. Okay, and we divide it by 4.4. And get a value of 0.55, let's say 0.6, something like that. 0.6. And okay, this damper constant connects velocities with forces. So we have this unit newtons divided per meters per second. Okay, so this comes what is needed in friction force or something is B multiplied with velocity. Well, then we have these elements, and okay, we are already so far, then you could determine at least the electrical values from the mechanical values, and I think we have already opened the correct slide here. So, for example, for our mass, the mass becomes this capacitor, and the formula is the actual mass divided by alpha squared. So then that's right here. Mass becomes capacity, and that is 9 grams. And then divided by alpha squared. Divided by 5.6. 6 and is squared. Okay, so this is a small value, and I see here in e minus 4, that means it's 10 to the power of minus 4. Yeah, we could write it like this, or we could write it like millis, micros. Let's write it in microfarads. So I multiply this with 1 million. Okay, and that's the value in microfarads and approximately 300. Okay, this is a usual value, let's say, so seems plausible. Okay, so the next one, L. What is the value of this inductivity in the model? Alpha squared divided by k, so 5.6 squared divided by, and k we calculated it as 660. So this should be the value in henries is the unit of L. So this is 47 million. Let's say 50, just to get the round number. Okay, so let's say this is 1 over k, okay? Becomes an inductivity, and this is around 50 millihenries. And the last one is the value of the resistor, and this is alpha squared divided by B. So again, 5.6 squared, and divided by 0.6 for the approximate value. So we have here 52 ohms. Okay, so the 1 over B becomes the resistor, and that is 52 ohms. And well, here we have 2 times R, so maybe this should be RB or something. So make clear that it's not the electric value here, this is the serial RS, which we found in the data sheet, 5.6 ohms. And the interesting thing is the mechanical effect is much larger. And well, that means when we have a resonance and C and L are, let's say, cancelled out, and only this large resistor remains, then we could really measure here the sum of RS, okay, probably also a little bit effect of LS, and R. And it means yeah, approximately 60 real ohms, not just 5 ohms. And let me see if we can see something like that in the data sheet. I think there are some curves. Yeah. The green curve is impedance, and the units here given on the right side. And for resonance, we have this peak, we have the maximum, and actually, yes, okay, in this special curve, we have a little bit more than, what would it be, 60, I think, a little bit more than 60 ohms. And I think with that idea, we know where it comes from. It's the sum of these 52 plus 5.6 plus some measurement errors. But that's why we have not only these 5 ohms. And probably they are using a loudspeaker with a little bit more of electric resistance, because there's a minimum of the impedance, and that's probably the value of the coil itself. So of just the wire, and this seems to be, well, no, it's nearly correct. It's 6 ohms, so we are very close to these 5.6 ohms. No, I don't know where the differences come from, but maybe they have a little bit more of damping. It's just one measurement, and typically in the data sheet you get an average value of many loudspeakers. Okay, so, but it seems at least reasonable. And I would say then we can leave it at that. Now, we could do more with this. So, for example, we could now program this in MATLAB. We learned about LTI system commands. We could define the total impedance as a transfer function. We could then determine the frequency response and many things more. But let's not do this. So instead, let's go on to the, are there any questions about that so far? That's okay so far. Good. Okay, then next thing is we can produce a sound by blowing over the neck of a bottle. So wait, I blow the bottle this time. That's it. And when I blow over it, then you can hear a sound. Okay, and it's a certain frequency, and we can calculate this frequency. And for this we just need some mechanical values, and they are given here. It's exactly the values of this bottle here. So the neck has a cross-section area of 3 square centimeters. Okay, so the opening here, 3 square centimeters. And it has a certain length of 8 centimeters. And then we have a main chamber here with a volume of 750 cubic centimeters. Okay, so how do we do that? First of all, we already have one formula here, which we need, which we can leave. This is the resonant frequency if we have model values for an L and a C. But we need an L and we need C. And what is the formula? And we find that in slides. And then we said there are some network elements, so for some networks. And so there is inductivity, and you could say inductivity plays the role of a certain package, that means a mass of air or something, which can be moved, which is not compressible. Yeah, that might be a surprise because air is normally compressible, but if air moves in a pipe, then actually there are packages which just can be moved around and which get not compressed. So if you apply a force, if you apply a pressure, then the whole package just moves, but it does not compress. Nearly not. Okay? So you can neglect that. And so what happens if you have a pressure? Well, this package of air is a mass and becomes accelerated. So it has to do with Newton's law of inertia. And actually, I think that's where the formula comes from. We didn't show it. I just wrote here down this formula, and we just said, okay, these mechanical values here, they correspond to an inductivity, but well, where does it come from? We could at least try to understand them. You're not asking something? It's just it's okay. It's okay. Then it doesn't come from. Okay, here's a formula which is an impedance. So we have a ratio of pressure, and Q was the so-called volume flux. That means there's a certain volume. The volume changes in a certain time, or we transport a certain volume in a certain time. And the ratio is this volume flux Q. And we have formula delta y q is, and then we have this strange s, which is the Laplace variable, s multiplied. We can always replace this with a j omega, so we understand there's a frequency in it. This stands for the s. And then we have rho is the density of air times L divided by A times Ln divided by A. And then let us see what we can do here. Let us multiply the Q on the right side. And then we have, well, what can we find here? Q is not just a change of the volume. There's a formula for this Q. You can also say if you have this package and it passes through a cross-section area, okay, passes through, then we have a certain velocity of the air particles which are connected with this volume flux. And here we can see Q equals velocity times A. So instead of Q, we could write here velocity times cross-section area A. Okay, and then let's not cancel this. Let's put this up on the left side. The pressure difference multiplied with the cross-section area, well, pressure times area, is the force. So there's a certain force on this package of air in the pipe. Okay, so this together with this, delta B times A is force. And on the right side, what remains is rho times L times A. So I'm using the density multiplied with length and cross-section area. So this is obviously the volume multiplied with the rho is mass. That's the mass of the air package. I put it in this bubble to say quantities yield the mass. And then what remains? Not this one, this was part of the force. So what remains is j omega and the velocity. And wherever you see a j omega, this comes from a derivative. Okay, so this is the time derivative of an oscillation. And well, if we apply this to a velocity, what's the derivative of a velocity? Is acceleration. So this is just Newton's law, which is behind the formula. Okay. We didn't talk about that, but that is behind here. Okay, but actually we do not need this, which is the values for rho times L divided by A, because that's the inductivity which we then need for our resonance. That was the starting point, resonance. Okay, so L equals rho times L divided by A. And the pipe here is the neck of the bottle. Okay, so let's take the numbers. First of all, the density of air. Okay, it was given somewhere in the slides, not in the stars, but in the slides, as 1.3 kilograms per cubic meter. So value is 1.3 for a rho. Then we multiply with the length. The length was 8 centimeters of the neck. 8 centimeters. We which is 0.08 meters. And then we have to divide by the cross-section area, and I think that was 3 square centimeters. Okay, the opening here, 3 square centimeters. So that's the question now. How many decimals are that? I think it's 1, 2, 3 zeros, and then 3, because 3 squared. Centi means 100, and that is squared. So we have 100 squared, and then meters remain also squared, and this is then 0.000 and 1. So I think this should be right. 0.003. Okay, and that is a value of 357. And normally this should be something mechanical. Okay, so this is something to do with kilograms and meters and seconds. But as an analogy, we say this should become inductivity. So now I write here Henry, which is not correct. Okay, we have no factor which transforms units. The units of these terms are mechanical units. But we can say, if it's just an analogy, let's take the number and replace the mechanical unit with the corresponding electrical unit, which is Henry.
Sir, why is 57 and 47 there?
Oh yeah, thanks. Oh, this is 4. You're right. 47. Okay, and then the acoustic spring, well, that's just a larger volume, where we can compress the air. So we do have a change of the pressure here, due to changing due to a flux going into or out of this volume. And here we can say this in the black bubble corresponds to a 1/C electric. So the capacity itself would be volume divided by rho and C squared. By rho and C is the speed of the sound. Okay, so again, this is just something mechanical, so it has mechanical units. But I will just take the number which comes from this and give it the unit farad, because capacity has farads. It's not correct, okay, but we are not mathematicians here, so we're just engineers in practice, so that's just it. Okay, so we need volume, and that was 750 cubic centimeters. Again, the idea, what is that in cubic meters? Okay, 70 is 100, but now we have it to the third. So we have 100 to the third. Okay, so we have divided by 1 million, you could say. This value divided by 1 million, and then we have cubic meters. So 750 divided by 196 is 1 million. That should be the volume in cubic meters. Okay, then divided by rho. 1.3. And the speed of sound. Okay, it depends a little bit on the height, but in the slides we said around 340 meters per second. So then let's divide it by 340 squared. And then we have a value which is very nearly 5, and then we have 10 to the power of minus 9, which would be really nanofarads. 5 nanofarads. Again, in millifarads, okay, these units will not give farads. We would need a transformer factor. We don't have that here, but electrically we can just assume this. Okay, and now we have what we need for our formula. The resonance frequency. So we multiply L with C, and we have 347 multiplied with 5, and that was E. It was 10 to the power of minus 9. Okay. Then we need the square root of times C, square root. This is the square root. Then we have to multiply this with 2 times pi. Times 2 times pi. And then the inverse value, because the resonant frequency is 1 over everything. Okay, and then we are here at 121 hertz in theory. So, this is 121 hertz. Okay, we heard the sound, but is that really 120 hertz? So we could measure it, and that's always important. Always verify your models, never believe the numbers. So we have something like a frequency analyzer here, and this program just works on the microphone of the computer. And we can see here frequencies. It's very small, sorry, so the last row is really difficult to see. We're starting with 20 hertz. Here's 100 hertz, a kilohertz, and up to 20 kilohertz. Okay. And when we hear nothing, it's probably because we have external elements. I need to go back to the internal microphone. Okay, so the microphone is here. Somehow the system is taking external values because we have coupled here over the HDMI connector. But where can I change that? See something? Okay. And now it works. So now what we see is this mountain range is me speaking. Okay, now we hear nothing. And this is again me speaking. So My language contains nearly every frequency between 20 and 20,000 hertz. And now let's see. We said this sound from the bottle is around 120 hertz. Here, this is the 100 hertz. And now I try to be as soft as possible and just blow on the bottle. Yeah, and I think it's not just approximately, it's really exactly these 120 hertz. So this is really, my measurement confirmed that what we did is not just theory, this is really practical. And well, this is amazing because we said before, normally you need a device with dimensions around the wavelength of the sound you want to produce. Okay, so if you want to produce 120 hertz, well, that has a wavelength, and there's a formula for a wavelength. I never can really remember it, but I know the speed of sound, small c, has the unit meters per second, of course. And I know in the formula occur the wavelength and the frequency. The wavelength has meters, so that's what we need on top. So we have the wavelength. And what we still need is divided by seconds, which is a multiplication with hertz. So we have to multiply this with frequency. So going back, we are interested in the wavelength of this frequency. And here we said this is around 340 meters per second. So this. The number is c divided by frequency. 340 meters is the c, divided by 120, well, doesn't matter. Huh? So we are around a little bit less than 3 meters. And for a body is enough, it has the length lambda by 2. But still, so this is half of the wavelength, it's around 1.5 meters. Not just here some 20, 30 centimeters. So it's amazing that we can produce such a deep sound with such a small device. Normally, it would be something like this. This has 1.5 meters, and the classic method to produce a sound here is just trying to use a standing wave here. So one of these strings should vibrate, and then we have here half a wavelength. And let me see. You can also produce that. There are lots of sounds in this, but there is a maximum. So let's see again. Okay, you see it, it's between 100 and 200. Okay, so the maximum here, let's say 150 hertz, and that is because we have not really 1 meter and 40 centimeters, it's just 1 meter and 20 centimeters. So we have this higher sound. Actually, for this 120 hertz, we would need something which is still larger. So that's a nice thing. We can produce sounds with much smaller dimensions with this effect. And in order to calculate this frequency or the necessary dimensions, we can use our models. So that's nice. Okay, then I think we have covered everything. Okay. Let's still draw an equivalent electrical circuit of the situation. And a special question, which role plays the blowing over the bottle? Okay, so first of all, we have this length of pipe, which we identified as an inductivity in series to the main body, which is a kind of capacitor. So we have a serial L and C. Let's start here. We have the serial L and C. And this is the neck. And this is the main body or the main volume. But there's more to it. If you can hear something, then there must be a source in the system. And yeah, well, I have to blow over the bottle. And you could say, well, I produce sound waves, I produce sound pressure. And that means I have here a source. Yeah, sound pressure. Pressure has to do with forces. Forces usually modeled as voltages. So we have here a voltage source, and this is my sound pressure. And these are vibrations, but not just one vibration. So what I produce with my blowing is a wide range, is a noise with many frequencies included. And this is attached here. So we could draw here this tilt. That means it's AC, but not just one frequency, many frequencies. Yeah, let's see how many. So we already saw that the speaking has this very broad band. Yeah. But just blowing. So is broadband. So a lot of frequencies are excited here. Most of the frequencies are damped because for low frequencies, this is, let's say, a disruption. It doesn't let anything through. For high frequencies, this is a disruption. It doesn't let pass anything. So only for the resonant frequency, this seems to be a short circuit now, and we have serial elements, and here we can add the impedances up to 0. So for the resonant frequency, we get here an impedance of 0, and then even for a very small amplitude of a pressure, we get a high volume flux. And that's what we can hear, high volume flux amplitude. So for the resonant frequency, then we get this volume flux Q corresponding to a current. That's the important part here. Blowing over the bottle, that's the source, broad AC source. Okay, but then we are really through it, I think. Any more questions on that? Okay. Then I'd like to look into one more situation which is still a little bit like mechanical, or it has to do with mechanics, let's say. And it's also quite similar to sound and sound elements, and it is hydrodynamics. And I think there's not really much new here. So I think all the methods we will see here, we will encounter in a minute, we have already learned, but yeah, hydrodynamics is often used in mechanical systems, and we need to get an understanding. And we can again apply our two tools. We can build equivalent electric models, or we could find differential equations and model them in CDE. So either way, let's look at pressures. and volume flux in these hydrodynamics, but we have to look a little bit more in detail what is a pressure, or what kinds of pressure are there. So the first kind is the static pressure, something that doesn't change. So let's say we have here a disk, for example, just a disk, anything, and for whatever reasons we have a pressure on this disk. Could be, for example, the weight of something else which presses on it. It could be acceleration, whatever. So let's just assume we have a pressure, and that means on this whole disk we will also have a force. And if due to this pressure the disk moves for, let's say, a very small distance, dz is close to 0, okay, well, then we have acted a small bit of work, mechanical work, which is then force multiplied with this small displacement. And well, the force is the pressure multiplied with A. That means if I replace the force here with the P, we have the factor A, and A is the surface of the disk, and the surface multiplied with a small length is a volume, a small volume. So we have changed, let's say, or we have passed the volume dV. And the next one is an interesting formula for interpretation, and one we will use 2 or 3 slides further again. Namely, when we divide this very small amount of energy that we needed to move the disk by the very small volume in which the disk moved, we get again this pressure, and it means we can interpret pressure as a kind of energy density. Okay? Energy which is somehow stored in a volume. Okay, so that's just one idea here. But where does the pressure come from? Yeah, we said one possibility is the weight of something else which is on top of this, and that means it has to do with a certain mass. And well, the mass comes from the density of the material on top of our disk. So on the bottom again you see the disk, density of this material, and then A is the area of the disk, and the height of the material here then is makes the volume. Okay, so we have a certain mass, and mass multiplied with gravity is then the weight force of this material on the bottom surface, on this disk at the bottom. And this is the static pressure, and so everything put together means we have here rho times g, so density times the gravity, then here we have the volume, and then maybe again divided by the area so that we get not the force but the pressure. And there is another term here, because in addition to just the weight, we could have an additional force, an external force, F, wherever it comes from. So additional force, F, and that would just add to the weight. So if we have an external force, then the static pressure is increased with F divided by A. When we do our analogies with the electricity, then we're always looking for a potential quantity, say that has to do with the voltage, and another one, the flux quantity, where something flows, which has to do with the current. And the question is that maybe already our potential quantity, which has to do with voltage? Yeah, the answer is no, because there are more kinds of pressure, but before we come to that, a little bit more about these static pressures. So let's assume we have have here a tank, an open tank, which is filled up to a certain height h with water or anything. And due to the weight of the water, we have an increasing pressure. We go down from the top level down to the bottom of the tank. So let's assume we have here, it's just an idea, we have here a certain volume within the water, and there is a pressure due to all the water on top, not what is below. So this small thing here just feels what is on top. It does not feel what is somewhere here to the left or somewhere to the right. It feels how much height of water is above it. Okay, so you could say the static pressure here at this point is then, we already saw, rho times g is necessary, and you have to multiply it with the height. So in the round brackets, that is the distance above our Q, or wherever it is, above. It's h minus z. So depending on z, we have an increasing pressure maximum at the bottom, of course. This pressure acts in all directions. Okay? Although it comes from weight, which only goes in the direction of the center of the Earth, this static pressure pressures in all directions. So, for example, we cannot feel this weight only on the bottom plate, but here also close at the wall. Exactly the same pressure. The pressure does not depend, as we said, on what is left or right. And that means the special shape of our tank does not play a role. It's only important what is the height of water on top that determines the pressure. So, for example, here we have a highly irregular shape, but you can calculate the static pressure on the bottom just by taking the height. Doesn't matter, there are changes in the cross-section area. It's just important what height do we have here. So the static pressure is rho times g times h. Same here. We have a large vessel, and let's say just a small pipe here at the bottom, and nonetheless the pipe defines here most of the pressure because it's so high. So for the static pressure, the complete height is important, and that we have a change of the surface here does not matter. Okay, just the height. So the static pressure is again just rho times g times h. Okay, so static pressure is not yet what we are looking for our analogies, because there is a second type of pressure. And you know that when you have running water, let's say in a stream or so, and you put your hand inside, you feel something, you feel force, and that means you feel the pressure on your hand. Well, and that is because we have moving particles, moving water molecules, for example, and they act a certain force. Well, a force spread over a surface is a pressure, and that is the kinetic or dynamic pressure. And well, how can we calculate this best? Let's say all our water molecules are very, very small masses. Let's say they have a tiny mass dm, and they have a kinetic energy. And this small kinetic energy is then just their mass by 2 multiplied with their velocity squared. Okay, just a classical kinetic energy. The mass has to do with the volume they're taking up, so which is also a very tiny volume. Okay, so here we can say mass is, or dm is density times a very small volume. And that means here we can write on the very small kinetic energy is rho by 2 times velocity squared times v. And now we can just divide this very small volume, and we get here an energy density, you could say. And as we defined 2 or 3 slides ago, an energy density can be interpreted as pressure. In this situation, this is then the dynamic pressure. So that's just rho by 2 and velocity squared. Okay, so, and in a complete system, we have static pressure plus dynamic pressure. So we have a total pressure, and that is the potential quantity we need for our analogies, not the total pressure. Well, we can measure these kinds of pressure individually or together. And yeah, you can do it, for example, here we have a big pipe, okay, and we have a stream of water here. Here we have one opening with a small pipe going upwards, and it's just an opening. And in this opening, okay, or away on this, across this opening, we do have a movement of the water, which has a certain dynamic pressure, but dynamic pressure is not felt upwards. Okay, the dynamic pressure is felt only if I put something here in the way of the water flow. So here we cannot feel the dynamic pressure. So what we can feel, what we still can feel, is the static pressure. And that's why we will get here an increase, a rise of the water up to a certain height, h static. Okay, so behind this must be a certain pressure, which we can calculate. P static is rho times g times this h. And so from this, from this height, you can calculate the static pressure in your flow below. The second one is also a pipe and opening, but this is bended. And yeah, it should be a very smooth bending. So that means here at the inlet, we can really feel both. We can feel the static pressure, but also the dynamic pressure. Now this is carefully redirected upward. Let's assume we have no losses, which is not true, but let's neglect losses here due to the bending. And the pressure which rises here up to a certain height as water, then means in this total height we have included both the static and the dynamic pressure. So that means we get this total height due to the sum of both. That's the total pressure divided by rho and g. And if you measure both, the total pressure and only the static pressure, then the difference, of course, yields also the dynamic pressure itself. So all 3 kinds of pressures can be measured. That's the important thing here. Okay, so that's the first quantity. The second one is always a flux, something that flows. And of course here we transport mass, molecules of water or oil. And interesting thing here is the mass cannot be produced and it cannot vanish. Mass is continuous. And mass is always proportional to the volume, because in fluid, like water or so, that can really not be compressed. Okay, so the mass is always proportional to the volume. And it means a certain volume you're moving anywhere in such a system of pipes means everywhere else the same volume is transported. And that means here this volume flux. That means a transported volume, or change of volume with time, that is everywhere the same. So it's constant, it's not constant over time, of course, it's constant over space. everywhere the same volume flux. And that means, for example, if we have here a larger pipe with a cross section A1, and we move the water here with a certain velocity, then in a certain time we move a certain volume. And then here we have a smaller pipe connected, that means a smaller A2. And to compensate for a smaller cross section, we need a higher velocity of the water in that part, because we transport the same volume. So we can see we have a continuity equation at any place. Velocity times cross section is the same, and this is also what we define as the volume flux, because it's not just a derivative of volume with time. We can also calculate this as velocity times cross section area. Okay, so then we have identified two quantities, and then let's just take a look here at what we can do with this. Well, first of all, let's say we have a tank which is filled up to a certain height. At the bottom of the tank we have an inlet or outlet, whatever, and there we will feel a certain pressure. Could be static pressure due to water which is stacked on height, but it could also be dynamic pressure if we put water in or out through the inlet. Anyway, we have a change of volume here, that means a volume flux Q from in or out. And now we have our formulas. We know the static pressure, at least. The pressure is rho times G times height. We have the height, in this case, if it's a straight tank. We can write the height as a volume divided by the cross-section area. Now, really only if it's a straight tank, yeah, that's clear. And that means the pressure here has to do with the volume. If you change the volume over time, we have a V dot. That is the flux, the volume flux Q. Okay, so we could put a dot here everywhere on top. That means we change the height, we change the volume, and then immediately we can replace this V dot with a quantity, with Q, and then we get an equation for the change of the pressure, which is connected with the volume flux Q, or it is ratio inverse on the other side. Q equals, well, something, okay, some mechanical quantities times the change of the pressure. This is somehow similar to electric things, and if this has to do, so if the volume flux has to do with current, and the pressure has to do with the voltage, but it's the derivative, so we have derivative here of a voltage, then this is similar to a capacitor, electrical capacitor, and that is, in order to equation, we have here capacity, so this here is the capacity, and that's where this term comes from. Okay, cross-section area of the straight tank divided by rho mg. If we have not a straight tank, so for example here we said, okay, static pressure depends on the height but not on the shape, you could still model it as a capacitor, but then it's non-linear. The capacity itself depends on the height, and actually there are also electric capacitors which are non-linear, so it's not a contradiction to electric elements, but let's assume we have straight tanks and then we have a constant capacity. Okay, then again, if we look into a pipe, then we have a certain mass package of water, a mass, and if we have pressures inside, then we have forces, and they can accelerate your package of water. So this has to do with inertia. So the basis here is we have an inertia force, or force for acceleration, which is m times the derivative of velocity is acceleration. Well, then some more things. The force is due to a pressure over the cross-section area called A here. Then we have the mass, okay, spread into a density, and the volume, length times cross-section area. Then the V dot is just reproduced. And when we take together the area A and the velocity, that is the volume flux. Okay, and when we have here a V dot, then the result is the Q dot. Okay, but this takes just together A and V dot, these two. Okay, then when nearly there, we already have this formula between pressure and Q. This time it's a Q dot. So here we have differing pressures on the left and right side. This is like the difference of voltages, which has to do with the change of the current. And here we would need then an inductivity. So everything here has to do with inductivity. Okay, and then again we could, oh sorry, some are writing. Even with these two elements, we could already model some situations. For example, here we have two tanks which are filled with different heights of water, because on the left side we have a pump, and this is, let's say, a source with a constant flow, that means a constant volume flux, Q0, which fills up the left tank. Then here, connecting with a pipe and a valve, which is just for opening or closing the pipe. So it's just like a switch, nothing more at this point. Then we could understand this electrically as, well, the first tank here is a capacitor. It's filled up to a certain height, that means with a certain pressure, and electrically means this capacitor has a certain voltage. Let's call it U1. On the other side we have another tank filled with another height, maybe less, maybe more, depends on the valve. And that means the height 2 becomes a pressure P2, and that is the analogy of a voltage U2 across this capacitor. Between we have the pipe with some mass of water in between, here in this pipe, and that acts like an inductivity. And the valve is just a switch which can open or close. And when we close the switch, then we have here a system with capacity and inductivity at the source. So there might be something trying to balance out, so that in the end the height on the left and the right side should be the same. But whenever we have L and C, we would have oscillations. So that's the reason when we open the valve, then the height H1 and also H2 might show oscillations. That's an explanation, and something that we can easily see here with the electric component. Then, then, sorry, I wanted to do something else, and that is I was asked to perform an evaluation, sorry. And for this, so let's stop with this, let's go on with that next Monday. And for the evaluation, I got a QR code and was asked you then to fill out questionnaire. Okay, so this should help us to improve everything.